Okay. Yeah, let's start the next talk. The speaker is Tomonori Ugajin from YITP. He will tell us about the entanglement between two disjoint universes. Please start.
All right, thank you. Usually, the speaker starts by thanking the organizers, but I am one of the organizers. So instead, thank you for everyone for joining the conference. And I hope this conference is fruitful for everyone. Today I'm going to talk about, as Nomura-san did, I'm going to talk about recent progress in understanding the black hole information loss problem. And okay, so this talk is based on basically 3 papers. The first two are with sorry. Okay, yeah, my pencil is working. Okay, the first 2 are based on work with BJ Barasubramanian at Penn, and Arjun Kar, postdoc at UBC. I think he's in the audience anyway, and some work in progress with Akihiro Miyata, hopefully appear in this month. So since Nomura-san nicely summarized what was the information loss problem is, so I don't need to talk much about this information loss in detail, but anyway, it's good to review it again for the people coming from a different field of physics. So let me review the black hole information loss problem in my way. Yeah. So what Hawking found in mid 70 is that the black hole can emit thermal radiation. So this is a cartoon for this Hawking radiation. I have a black hole in the middle of our universe, and it emits thermal radiation. And there's a intuitive way to understand this why the black hole can emit Hawking radiation. And this is the cartoon for explaining the basic mechanism for the Hawking radiation. So this left side depicts this black hole and its interior, and right side is the exterior of the black hole. And we are considering a quantum field theory on this black hole background. And this, the states of this QFT is the vacuum. And it is well known that in the vacuum of a QFT, the pair creations of particles are happening everywhere. And so in particular, so by this particle creation, the pair creation, one positive energy particle is created, and one negative energy particle is also created in pair. And so without any horizon, then okay, this negative energy particle is kind of unstable. So these 2 pairs are annihilated again. This is basically this Heisenberg uncertainty principle. But the situation is different when the horizon is present. Namely, this negative energy particle can be absorbed to the horizon, and it gets stable. And so as a result, the mass of the black hole is reduced by amount of this negative energy that this particle has. And as a result, the mass of this, the black hole decreases as we increase the time, because this pair creation happening at the constant rate each time. So and this, this positive energy particle can escape from the horizon, and we can see this as a radiation emitted from the black hole. This is the basic mechanism for the Hawking radiation happens, and this is the reason why black hole can lose mass. due to this radiation. But this is a very problematic process because of the following reason. So this is because the pair of particle created in such process is entangled, almost maximally entangled. So once so such negative energy particle goes into this horizon or black hole interior, then it contribute then the entanglement between this interior of the black hole and the exterior increases a little bit. And so since this kind of pair creation happens at constant rate, and this means that this entanglement between interior of the entanglement between black hole interior and exterior is linearly increasing in time. And so we have obtained two plots. The size of the black hole is decreasing as time evolves, but this entanglement between black hole interior and the exterior is increasing. And these two plots are in tension. This is because of the following reason. So in quantum gravity, the dimension of the Hilbert space of this black hole, now the dimension of the Hilbert space of the black hole interior is given by the entropy of the black hole. So this dimension of this black hole Hilbert space is given by e to the s of this black hole entropy. And as we saw in this first plot, the size of the black hole is decreasing due to this evaporation. So this black hole entropy is decreasing. So the dimension of the Hilbert space of this black hole is decreasing as this the evaporation proceeds. However, the entanglement between this black hole interior and the exterior increases as the evaporation proceeds. And so this so if I naively trust the Hawking's calculation, then this entanglement between interior and the exterior gets larger than this, the entropy of the black hole, which is impossible in the unitary theory of a unitary quantum mechanics. So this is a version of black hole information loss problem. And so what is the correct behavior of this entropy in the unitary theory? Well, instead, the Page argued that in a unitary theory, the entanglement should behave in the following way. Depends on the asymptotics of the black hole. And okay, so here I plot the entanglement entropy between this black hole interior and the exterior as a function of time. And so this, that at the initial time where soon after this evaporation starts, this entanglement entropy is linearly increasing in time as Hawking predicted. But after the certain time scale, which is fixed by this the entropy of this initial black hole, which is so-called Page time, then this that the entanglement entropy must saturate. So this happens for the case of black holes in anti-Toshiter space, or this entanglement entropy linearly growing initially, and then after after this Page time, the entanglement entropy start to decay or decrease. This can happen for really evaporating black hole. Like black holes in asymptotically flat space or Toshiter space. And okay, so Page argued that okay, so this kind of behavior happens should happen for evaporating black hole by using the some toy model. And so the question since then has been that okay, how do we understand the this late time of this page curve from this semi-classical gravity point of view. And okay, I'm going to talk about it in this talk. And so there has been recent developments about this. I mean, understanding page curve from a semi-classical gravity point of view. Okay, the punchline of this development, I think, is the following. So the usual rule for the entropy computation in quantum field theory, okay, so this is known as replica trick, gets modified in the presence of dynamical gravity. And this results in a new formula, which computes this, I mean, the entanglement entropy in the presence of gravity in a proper way. And the result is known as this island formula, which was spelled out by these papers. And it turns out that this resulting island formula can successfully reproduce the page curve of the black hole. I mean, the late time part of this the page curve for the late time part of this page curve. And so in this talk, we will discuss a version of the island formula applicable to any black hole. So this is the introduction. And so let me explain the setup of our system. So we start from two disjoint universes. And for simplicity, okay, say universe A and universe B. Okay, so these are disjoint, meaning that there is no exchange of classical information or any interaction. And okay, so on this universe A, I define some quantum field theory. And in order to simplify the discussion, I restrict myself to the class of QFT called the conformal field theory, but it's not so important. And in addition to this, on this universe B, I define the same quantum field theory, but in addition to this, I turn on gravity in this universe B, and okay, which I choose to be semi-classical. And so to further simplify the discussion, I will restrict myself to the case where these universes are 1+1 dimensional, but hopefully the generalization to higher dimensional case is straightforward. And so as a result, the Hilbert space of this, I mean, the two disjoint universe system is the tensor product of this the Hilbert space on this universe A and the Hilbert space on this universe B, on which this gravity, semi-classical gravity is acting. And so we can choose this, I mean, the gravitating universe to be anything we want, asymptotically flat or ADS or de Sitter space in this setup. And okay, so in order to study this the black hole evaporation, we will place black holes in this gravitating universe, and what happens for the entanglement entropy in the presence of such a black hole. And okay, so the similar setup was considered in a recent paper by Hartmann, Jan, and Chagurian, which appeared at the same time, basically. And so yes, so okay, as I said, I defined a classical, semi-classical theory of gravity on this, I mean, that the universe B. So let me specify the action of this semi-classical gravity in particular. So I choose this JT gravity action. For this purpose, I choose this JT gravity action in this gravitating universe. And it involves two fields. One is this metric, and the other is the field so-called dilaton. And the action of this JT gravity is basically given by this. So this Einstein-Hilbert term times, I mean, that times this dilaton profile. And so this JT gravity action is one can think of this, I mean, the JT gravity action as a dimensionally reduced version of this higher dimensional gravity system. For example, if I start from 4D near extremal black hole, whose metric is looks like this, and this, I mean, RT component of the metric is promoted to some dynamical field G mu nu, which appears in 2D after the dimensional reduction, like a G mu nu. And this phi, this, I mean, the volume of this transverse direction, which I denoted by phi, the dilaton, appears in this way in this 2D Lagrangian. So since the okay, so in the later of my talk, this the fact that this dilaton field phi the measures this the volume of this transverse direction is very useful, and in particular the value of this the dilaton at the horizon of the black hole basically measures this, I mean, the area of this black hole horizon. So this dilaton plays a role of this black hole entropy in this JT gravity setup. So okay, so having specified this, I mean, the theory of gravity in this system. Okay, so let me specify the state on this disjoint universe setup. So on this bipartite system, we consider the following some field double-like state. So these I's are the states on this non-gravitating universe, and okay, and these psi I's are the states of this CFT on this gravitating universe. And for simplicity, I choose this, I mean, that for convenience, I will choose this, I mean, that the psi I's on this universe B to be the energy eigenstates of this conformal field theory on this gravitating universe. So it is an eigenstate of this Hamiltonian on this CFT on B. And okay, so these tensor product states are weighted by this e to the minus beta, the energy of this states in this universe B. And so this, I mean, that the state has a dependence on this, I mean, temperature, which appears like this, as in this sum field double state. And so the question I would like to ask is that, okay, how this entanglement between these two universes are changing as we tune this entanglement temperature beta. This is a question I would like to ask. So in order to study this, okay. So what I want to compute for in the following is this entanglement entropy of this universe A, or which is defined by the von Neumann entropy of this reduced density matrix on this non-gravitating universe A. And okay, so this is obtained by tracing out this tracing out this the part of this gravitating universe. And so it has this expression. And okay, so the basic ingredient of this reduced density matrix is this overlap between two states on this gravitating universe. And so what I need to compute is this, I mean, that the overlaps or product of overlaps. And so when we turn off gravity on this universe B, then okay, this the state I am considering just reduces to this sum field double state, and so this entanglement entropy on A is reduced to this, I mean, summary entropy of this QFT on A. And the question I would like to ask is that what happens when this gravity is acting on this universe B, and how this result is modified due to this gravitational effect. And um, so to compute okay, so to calculate this entanglement entropy, okay, we use so-called the replica trick, and that means okay, so we that means that we first compute this linear entropy for this reduced density matrix A on A, and then take okay for positive integers n, and then analytically continue in n, and then okay, so then take a derivative with respect to n. In this way, one can calculate this von Neumann entropy of this reduced density matrix on A, and so okay, so so this is a traditional way to compute this entanglement entropy. So we in this talk we also employ this trick to compute this entanglement entropy, and moreover, this the linear entropy is nice in the sense that it can be computed by using the path. It has a path integral description, so we can use we can use the gravitational path integral to compute this linear entropy. So okay, so let me explain how we compute this linear entropy using gravitational path integral. Okay, it turns out that the linear entropy is computed by a gravitational path integral on this n copies of this gravitating universe. So so let me explain why this is the case. This this linear entropy has this expression whose main ingredient is this product of overlaps on this of the states on this gravitating universe B. And so since each overlap has a path integral description on this gravitating universe with specific choice of boundary conditions, which specify these excited states. And since we have a product of them, so this the entire linear entropy involves the path integral on n copies of this universe, n copies of this gravitating universe. So the first copy computes this the first overlap. The second copy computes this second overlap, and so on. And okay, so what we need to perform is this with the gravitational path integral on this n copies of this gravitational path integral on this n copies of this universe B with these boundary conditions specifying the excited states. And okay, so let me remind how do we evaluate. So in order to do this, let me remind how do we perform this the QFT path integral in the presence of dynamical gravity. First of all, so when this QFT is coupled to dynamical gravity, okay, of course we need to integrate out all these gravitational degrees of freedom. I mean, integrate over all possible metrics, which satisfies the given boundary conditions. In our case, these boundary conditions specify these excited states that appears in this overlap, particular overlap, which appears in this linear entropy. And okay, so this is a schematic way of writing the this gravitational path integral. We have an integral over all possible metric, and the integrand is given by this the partition function, QFT partition function on each metric, and with the weight factor basically given by this action of this gravitational over the gravitational sector. And of course, I mean, it is impossible to perform this full, the path integral. And so what the trick I want to use is this, that as usual, going to the semi-classical limit, namely this G Newton constant to 0, where this path integral is reduced to the sum of all contributions of this sum of all Saddle points. Okay, so in this semi-classical limit, this the path integral can be evaluated by the Saddle point approximation. Mean that by picking up the dominant contribution, which I denoted by GC, and okay, so each of these gravitational configuration extremizes this action of the effective action of this gravitational partition function. And okay, so we want to use this prescription to compute this linear entropy, which involves this n copies of this gravitating universe B. So in the problem at hand, there are many possible gravitational saddles which can potentially contribute to this linear entropy. So okay, so first of all, the one possible saddle, one possible gravitational saddle in this linear entropy is this. Just we have n copies of this universe B, which are totally disjoint. But since gravity is turned on this setup, so we can there are other solutions which satisfies these boundary conditions. Namely, we can connect that each copies of this gravitating universe by a wormhole. So for example, so here I depict the example of such wormhole connection. The first and the second copy of the gravitating universe is connected by the wormhole, this tube-like structure. And the others are still disjoint from the rest. And okay, so we can continue to connect these copies by wormholes. And the extremal case is that this extremal case is this configuration where all copies are connected by these wormholes. And so okay, so in principle, all these saddle points are contributing to this gravitational path integral for the linear entropy. But it turns out that at low temperature, this fully disconnected guy will dominates in the path integral, and in the high temperature limit, this fully connected guy dominates in the gravitational path integral. So so in this talk, to simplify the discussion, let me just focus on the contributions of these two guys. One is fully disconnected, and the other is fully connected. And so the resulting linear entropy, which can be computed by the gravitational path integral, has the two terms. The first term is coming from this fully disconnected one. the second one is coming from fully connected one. And okay, okay, the actual linear entropy is sum of them. And okay, so by using this expression of this linear entropy, we arrive at the following formula for the entanglement entropy by taking n goes to 1 limit. And so the resulting entropy involves two ingredients. One is so-called no islands, is no islands, which is just this CFT summer entropy or CFT entanglement entropy on this region A. And basically, this S-no island is coming from the contribution of this fairly disconnected saddle for the linear entropy. And the other ingredients of this entropy is that this S, which I denoted by S island, basically, this is the contribution of this fully connected wormhole geometry. And then, okay, so this actual value of this entanglement entropy is given by the minima between them. And yeah, so this is okay. As I said, is no island is just the entanglement entropy of this sound field double state in the CFT. And so let me explain. So how do we compute this S island contribution? It's a little bit involved, but you can compute like this. So we are considering a state on these two disjoint universes, A and B. And so this S island contribution involves an interval on this gravitating universe, which is denoted by C. And this this phi AC is the dilaton value on the boundary of this C or AC. And this is one ingredient. And in addition to this, we have the CFT entanglement entropy on this AC. So S beta AC is this entanglement entropy of the sound field double state on this A union C, and minus the vacuum the CFT vacuum entropy on AC as well. So okay, so what we first need to do is that the sum over these contributions entanglement entropy plus dilaton value at the boundary. Then okay, for all the possible intervals on this gravitating universe C. And then okay, we have to minimize over all possible intervals, extremize for all possible intervals on this gravitating universe. On the gravitating universe. And okay, the resulting the value resulting value is denoted by this S island. And okay, so this is okay, so remember that okay, so this dilaton value is related to this that area in higher dimensional theory of gravity is related to the area of this transverse direction. So actually, what is really meant by this phi is this area divided by 4G Newton. And so this CFT entropy here is that is related to the bulk entanglement entropy. Is related to the bulk entanglement entropy. So which is extremized with respect to all possible interval C. And so this is related to so HRT formula for holographic entanglement entropy in this ADS CFT correspondence. And okay, so the formula now only the difference is that now this HRT time type formula applied to the generic spacetime, for example, in the presence of black hole. And okay, so this is kind of natural generalization of this holographic entanglement entropy formula to all over possible gravitating spacetimes. Yeah, so okay, one convenient way to write this, and also this combination is sometimes called generalized entropy, as this, I mean, this bulk entropy part gives this quantum correction to this Wittgenstein-Hawking area term. Okay, and so sometimes it is useful to rewrite this generalized entropy in terms of in the following way. So we are starting from some fit double-like state on this AB, and we focus. We are talking about the entropy on this AC, disjoint union. And so since this some fit double state is pure on AB, so the entropy on this AC is equivalent to the equal to the entropy of this complement region C bar. And so in that way, this S island contribution is on this AC is rewritten in terms of this entropy on this C bar. In the actual computation, I mean, it is much more convenient to use this the second prescription. I mean, okay, so we first compute all possible generalized entropy on this C bar in the gravitating universe, and then extremizes over all possible intervals C bar. In that way, we can obtain this S island contribution. Okay, so the discussion involved a little bit technical things. So let me summarize what I have been saying so far. I consider the system where we have two universes. One is non-gravitating, and the other is gravitating. And I consider on top of this setup, I consider this kind of sound field double-like state. Where this degrees of freedom in this non-gravitating universe A is entangled with the states on this gravitating universe. And this amount of entanglement entropy can be tuned by tuning the entanglement temperature beta, which appears in this sound field double type state. And I argued that in the presence of gravity on B, the usual rule for the entropy calculation gets modified, and that new rule for the entropy calculation is given by this. I mean that okay involves the minima between these two terms. One is this CFT entanglement entropy, and the other is this so-called generalized entropy on this gravitating universe. And yeah. And okay, so that okay, the task. Okay, so in order to determine the actual value of this entropy in the presence of black hole, what I need to do is to compute this diatom value, which appears in this S island contribution in this new entropy formula. By the way, so this the region in the gravitating universe I introduced is a so-called island in this setup because so this non-gravitational degrees of freedom somehow okay this island is the region in the gravitating region in the gravitating universe which can be captured by the entanglement between A and B, and so this region is sometimes called island, which I probably use in the following. And okay, as I said, the next task to determine the value of the entropy is to determine this diatom value. And okay, so let me explain how do we calculate the dilaton value in our setup. And okay, in particular, the important thing is that this dilaton receives the back reaction from the state state of the total system. So we are considering this sum field double type state on this A and B. And okay, so it has a CFT stress energy tensor value on this universe B. And okay, so since okay, so so the gravity is turned on this universe B. So the space-time get back reacted due to this stress energy tensor profile. And so in order to determine the entropy, okay, we need to correctly, treat this back reaction, which is coming from stress energy tensor. And okay, so the simplicity of this JT gravity allows us to determine it completely. So this is a stress energy tensor profile on this gravitating universe B of this state. It agrees with the summer expectation value of the stress energy tensor. And the dilaton is determined by this simple equation, which we can solve. And okay, so let us first apply this island formula for ADS black hole. So without entanglement between these two universes, beta equal infinity, I assume that the black hole in the gravitating universe is just a usual ADS eternal black hole, which has only one bifurcation surface. And then, okay, so I eventually turning on this stress energy tensor on this gravitating universe B by adding the entanglement between these two. And then, okay, so because this stress energy tensor is turned on, this ADS eternal black hole gets back reacted from this stress energy tensor. And okay, so since we can completely solve this equation of motion, we know how this space-time structure is deformed. Okay, so what is happening is the following. Okay, by adding this stress energy tensor, this bifurcation surface splits into two pieces. And one is going to the right boundary, and the other is going to the left boundary. And as we increase this entanglement temperature beta, and as a result, the back reacted black hole has a very long interior region, which is so-called causal shadow region. Because this region is causally inaccessible from these boundaries of this ADS, and and then okay, so if we minimize, okay, so this is a resulting space-time, and we then okay, so giving this dilaton profile, we can plug it to generalized entropy, and taking extrema over all possible intervals in this gravitating universe. It turns out that this interval, which extremizes this generalized entropy functional, is given by the Cauchy slice of this black hole interior, and so the resulting S island in this black hole geometry is given by the horizon values of this dilaton profile, which is equal to the black hole 2 times black hole entropy. And so in summary, what we get for the entanglement entropy is okay. So since this the actual entanglement entropy is given by the minima between these two surface, these two contributions. So the resulting entropy as a function of this entanglement temperature is following. So in low temperature regime, okay, so this is no island gives this smaller contribution. So this resulting entanglement entropy agrees with the Hawking's prediction, which is linearly growing in temperature, 1/beta. But as we increase this the entanglement temperature, then this S no island gets larger than S island, which is given by 2 times of the black hole entropy. And so, so this means that okay, this the new formula tells us this entanglement entropy is saturated by the value of this 2 times black hole entropy. And so this is basically what we anticipated by the page argument. And okay, the resulting curve is nothing but the page curve for ADS black hole. Okay, so we can also apply this, I mean, that the same formula for black holes in flat space. Okay, so let us start from usual eternal Schwarzschild type black hole when there is no entanglement between these two. And then, okay, so let us increase the entanglement between A and B. Then, okay, so this the original eternal black hole is eventually back reacted. And okay, again, we can so again we can determine the we can completely specify this back reaction of the space-time. And and it turns out that the Penrose diagram of this back reacted for black hole is the following way. Is the following. Okay, as in this ADS black hole, okay, we have a very long interior region. Right. Okay, so the net effect of this back reaction is lengthening this black hole interior region, and which is again identified with this island or C in this setup, and and also it also turns out that the area of these bifurcation surfaces in the case of flat space is given by some the value some constant value minus the temperature or entanglement temperature we are turning on. And so this means that as we increase the entanglement between these two universes, say A and B, then this area of these black holes are decreasing like this. And so as a result, by plugging this result to this island formula, which computes this entanglement entropy, again, what we get is following. So first, linearly increasing, which is coming from this no island result, and then okay, so late times this island contribution dominates, and so since this is given by the black hole entropy, which we found to be decreasing as we increase this entanglement temperature. So this entanglement entropy starts to decrease as we increase the temperature instead of saturating to some value. And this is the consistent with the Page's prediction for the flat space black hole, namely that okay, so since in flat space black hole can evaporate, so the area of this black hole is decreasing. So the entanglement entropy has to decrease after the Page time. And our calculation correctly captures this decreasing part of this page time for the case of this flat space black holes. And we can finally we can do the similar calculation for Doshita black hole. In the absence of entanglement, we assume that the space-time is given by this kind of Schwarzschild Doshita type geometry, where we have two horizons, namely the black hole horizon and the cosmological horizon depicted by this yellow dot. And then, okay, as in the previous cases, we can turn on this entanglement between these two universes, and then then see how this space-time is get back reacted due from this stress energy tensor. And it turns out that again this black hole develops this long interior region, and this the cosmological horizon approach, and in addition to this this cosmological horizon approaches to the future infinity and the past infinity of this the space-time. This is what happens for the back reaction of this Doshita black hole. And this S island part is computed by this area of this apparent horizon in the black hole interior, and whose area is again decreasing as we increase the temperature. So we have this kind of page time. And okay, so this is consistent with the fact that Doshita black hole can evaporate, which is first, I think, first discussed by Busso and Hawking, and yeah, so we our version of this island formula also captures this effect of evaporating black hole in Doshita space. Okay, so let me summarize. Okay, so we discussed the entropy calculation in the presence of gravity in a simplified, at least two disjoint universes setup. And okay, by introducing as in the recent as all of these recent discussions, we introduced this replica wormhole to the calculation, and then found that this the version of island formula in our setup, and yeah, and right, and the results obtained are consistent with this. I mean, the argument of page, and yeah, so there are several things to do. For example, so we can generalize it to linear entropies. So in this talk, I just focusing on this entanglement entropy limit, but we can talk about this linear entropy or generalize it to relative entropy, and we can introduce some time dependence to this something double setup, or so okay. So ultimately speaking, we would like to know what is the microscopic origin of this island formula. All right, that's it. Thank you.
Thank you very much for this talk. So it's time for questions. So if you have a question, please raise your hand in this Zoom command, this reaction command. Or if that's difficult, just yes, please ask. Shinji has a question, please.
Yes, I have a stupid question. So I'm a bit confused about this Doshita black hole case. So do you recover Doshita entropy at the end?
No. Okay, so this entropy is coming from this black hole part.
But the cosmological horizon remains, right?
Yes. But okay, so this gives a larger entropy, larger contribution in the island formula. So we have to ultimately speaking, so if you have two horizons, then I need to choose the smaller one, which is now given by this entropy of this black hole part. And so this is
Yes, the formula tells so, but we still have a Dojita horizon, right? So why physically you should get something?
So this is because so we are considering where this the degrees of freedom in this Dojita space are entangled with this the non-gravitating system, and since this the Hilbert space of this Dojita black hole, the size of this size of this Dojita black hole is decreasing, right? As this black hole evaporates.
Sure.
So the entanglement entropy should decrease, and that's the reason why the entropy should decrease. Or okay, so if I consider the Dojita space without a black hole by restricting ourselves to this region, then okay, it saturates to this Dojita entropy. We are also commenting on this, but yeah.
I see. Okay, thank you.
Okay, any other questions? Izuka-san, please ask question.
Can I ask a question?
Sure.
So I just wondering the very simple question. Suppose we consider, say, asymptotic flux spacetime. Now we can consider the Penrose diagram.
Okay.
Even we can consider the evaporating black hole.
Uh-huh.
We can directly apply the island prescription.
Yes.
In this setting.
Yes.
On the other hand, in your situation, you consider two disjoint universe.
Right.
Where one is gravitational theory and the other is not.
Yes.
Can you just comment on what is a merit and demerit, or pro and con, comparing the single boundary black hole or your two disjoint?
Okay.
What is the merit of your situation compared with the usual single black hole situation?
Single black. Okay, you mean this? I mean that the black hole with bath setting.
In that situation, you can also do the island prescription, right?
Yeah. Okay, so one. I mean that. Okay, so one. I mean that not so important. I mean that the advantage is. I mean that. Okay, so in this. I mean that the black hole coupled to bath setting. I mean that we have to be careful about this definition of this entanglement entropy, right?
Right. That's we have to cut off the gravity.
Right. And the one minor advantage is that we don't need to care about it.
That's because you have a separate universe.
Yeah.
Is that the main difference?
And also I mean that so we can talk about talk about this Dojita black hole. That is also one advantage, I think.
We cannot directly do the considering single Dojita space and does apply the island. That doesn't work. Is that what you're saying?
Yeah. For example, you can add this. I mean that non-gravitating region like this. I mean that to the future of this black hole. But I mean, okay, the physical. I mean that. Okay. I'm not sure what is physically means. So I think yeah.
Well, I agree that if you switched off the gravity in that region by hand, it's very ad hoc situation. In your situation, it's more natural simply because you have a different universe.
Yeah.
But considering two disjoint universe is more or less ad hoc to me.
Well, I mean, okay, but this is what this basically this the Hartle-Hawking state does, right?
Yeah, I agree. But you don't see any more manifest difference other than what you said so far?
Yeah, right. And also one difference is that so in this that eternal black hole. Okay, I'm not sure the reason why, but this eternal coupled to that heat bath in the gravitating region. I mean, we saw this saturation, right?
That's because black hole is not evaporating.
Yeah. Right. But now, so here, that we have a result for this evaporating black hole. I'm curious about why this, the difference is, where this difference coming from?
Well, even in the asymptotic flux case, if you consider the back reaction by the Hawking radiation to make black hole to evaporate completely, I think you can do the same thing.
Yeah, the way, time evolution in this, the eternal black hole in the bath setup correspond to, that's solving this back reaction. So I'm just wondering, yeah.
Right.
Yeah. So.
Okay. Any other question? So can I ask one question about
Sure.
your Penrose diagram? You have this Penrose with two horizons, right?
Right.
And so how that solution appears? Is that exact solution to Dilaton gravity?
Oh yes, this is. Okay, we can always construct an analytic expression for these. I mean, the back reacted black holes in the Dilaton gravity.
So in that case, so the source is the energy stress tensor?
Yes. And so basically, what I need to do is solving this kind of equation. And okay, so now this is given by this stress energy tensor for the summer state.
I see. I remember something similar appears in genus-like deformation.
Yes, very okay. So the solution is, I mean, that the almost the same, because I mean that in this genus solution, okay. So what I have for
the question is that I think essential point you are adding entanglement, right?
Yes.
So but the genus solution we just put the scalar field.
Right.
Profile.
And
yes.
the scalar field, I mean, that contributes to this right-hand side. And so in the simplest case, this I mean that let's say chi, and okay, this stress energy tensor is constant for the scalar configuration in 2D.
Yes.
And so this is very similar to what we add in this.
I see. The equation is the same, but
the equation is
different state. State is different.
Yeah. So this, I mean, that general solution, we have two different, I mean, that boundary values for the scalar field. Right?
Yes.
But now, I mean, that okay, I'm just doing is turning on this stress energy tensor profile on this entire gravitating universe.
I see. But the metric is the same.
The Dilaton profile is the same.
I see. Okay, thank you. Yeah. And so, no more questions? If any, or if it's difficult to raise hands, then you can speak up. Okay, so if not, it seems no more questions. So yeah, we already had some interesting discussion already, and had a very excellent talks in this morning. And the next session in the afternoon, we will start from 2 p.m. And so we have some in Japan, we have a lunch break. Maybe some of you have a dinner for US people. Okay, so please have a rest. And thank you very much for participation. And so, okay, so finally, let us thank the speaker again. So we will close this session very soon. Thank you very much.
高柳さん。
ちょっと待ってください。はい。ちょっと待ってくださいね。ちょっとすいません。ちょっとだけ待ってください。ちょっとだけ待ってくださいね。どれだろう。ちょっとすいませんね。はい。